So we have some results. We can certainly see that there is a difference there, and we'll just see how they compare to the Inco figures there. So first of all, according to Inco, should be about 0, so titanium working okay. Stainless steel, a little bit more active there. Lead is a strange one, as I say, it never seems to work at all, and I'm sure that lead and tin are actually, lead at least, probably in the wrong position. Copper, minus 0.2, we've got minus 0.3, according to the Inco list. Brass, again, a little bit more noble than what the list would say. Aluminium, a little bit more noble. Zinc, 100 or so. You can see in each case there around about 100 millivolts out, probably because this is water just with salt in it. It's not seawater, it's not flowing seawater. We'll come back to that later on. You'll see that in fresh water we do expect different potentials there. But fairly straightforward process. Developing this, we can certainly see that there are differences there, and you can make up your own list in that way. So just showing you how that all works. Just unplug my little probe there. And just to show you what we were testing there, I didn't want to disturb it before, but there's all the metals from, going backwards in this case, so magnesium, the small one there, zinc, aluminium, brass, tin, copper, lead, stainless steel and titanium there. So that's how we work that. So while we've got that out, so Jackie asked me, am I going to be putting menthos in coke to make nice exciting explosions and things? So I'm afraid not. We can't really make any bells and whistles and explosions. What I will try to do is just have a look and see whether we can get some notes out of some of our little... Sorry? Yeah, no, it's all right, Raman. I've just this one off here. So we'll just see what happens if we have a look at some of the middle metals there. I've taken the probe out and plugged it into this little black box and switched it on. So there you go. So that's the Galvanic series according to Deep Purple, and just in case you weren't aware what we were talking about. So I don't suppose Humphrey Davy or PFT had any heavy metal with their heavy metals, so we'll take it at that. So we can see that galvanic corrosion works. We certainly have differences in potential there. We'll now have a look at some of these issues that we can't just use those potentials, the differences between them, and work out whether we're going to have problems. And the first bit of work that I want to look at was some very thorough work done for one of the Australian Standards Committees, and they produced a standard 4036 on galvanic corrosion. As far as I'm aware, it's fairly unique. There's no other similar one around the world at all. And what the work that was done there was have a look at lots of galvanic couples, and rather than just worry about the potential, work out the actual current that flowed between the two metals there. And they measured that current and divided it into 4 categories. So the way that they looked at it, they had a metal considered. So you have a metal, you connect a second metal to it, what is going to happen? And There's a number of things. First of all, you might be protected, which is the green one. You might have some slight corrosion. You might have a little additional corrosion, or you could have severe corrosion. They actually looked at 143 metal couples. These were all sorts of engineering materials and things, not the more obscure ones. And interestingly, of that 143, about 60% of them were either protected or didn't have any problems. So this whole idea that if you join a second metal to your first metal that you will have a problem, in 60% of the cases you probably won't. In fact, you might be protected. Of course, you will have problems in 20%, major problems, and another 10% or so. So we've certainly got to worry about that. But this first idea that if I join a second metal to a first metal, I'm going to have a problem is certainly shown up as not correct according to this very thorough work that this standards committee did. This is a table I've made of the results of the work from the standard, and I'm not going to go through it. It's a little bit busy there, but what it shows here, this is the metal considered. So these are some of the metals that they looked at, starting from zinc, aluminium, mild steel, etc., moving through various copper alloys, nickel alloys, and right up to the end there. And then you join a second metal, the same sort of metal there. And in each case here, I have each of these contact metals. In the first column there, you put a colour there showing what the potential difference is. So that if it's a very green, then it's very negative, so it's likely to be protected according to the Inco series. If it's very red, it's likely to be badly corroded according to the series. If it's yellow, then there should be little effect there. So that first column there, the greener it is, the more likely you are to be protected. So for example, any of these metals, if I join zinc to them, as you'd expect, they will be protected by the zinc. Aluminium, steel, much the same, and less degrees of protection for each of them there. The second column in each one is showing the actual current that's flowing according to the standard there. So if it's green, then it's being protected, or there's no current flowing. If it's red, there's major problems occurring there. And generally, it works out okay. The bigger the positive difference between the two metals, the more likely you are to have a problem. So as we would expect, if I join a copper alloy to zinc, you'll see there is quite a big potential difference, the first column there, and then where they've actually done a test, the second column there's a red mark there, so major problem. Join zinc to a copper alloy, you're going to have a major problem there. But you will see that it doesn't always work that way. So for example, the tin there, if I join copper to tin, you wouldn't expect too much of a problem according to the potential difference, but according to the tests carried out, there is a major current flow there. Similarly, if I join brass to tin. Also lead, as I mentioned, always a problem one there as well. So it doesn't always work, but generally the bigger the potential, the bigger the problem, but it's certainly oversimplified. So the main observations from this, the greater the potential difference, the greater the current flow. But, as we said, 60% of them don't show any problem there. Generally, you need to have at least 0.35 volts to have a major problem, although there's one couple, aluminium and 316, which was 0.7 volts difference and very little corrosion. And some couples showed corrosion with even a small potential difference, so it doesn't always work. So here we've plotted the potential difference. If it's negative, then it's being protected. If it's positive, it's corroding. And this is the 59% that's being protected or whatever. Most couples, not a problem. We're only getting corrosion. Some metals with a negative potential, still showing corrosion. But here's this aluminium with 316. Despite having a positive potential difference of 0.7, we're only getting minor corrosion. And here's another outlier, if you like, lead and tin with copper alloys, even though the potential difference according to the Inco series is 0, we're still getting corrosion. Certainly if you have a large potential difference, you're more likely to have severe corrosion, but it doesn't always follow.